The second type of chi-square test is a test for homogeneity of populations. Let's look at an example. Successfully breaking a cocaine addiction is incredibly difficult. 72 adults who wanted to stop their use of cocaine were randomly assigned to one of three groups. One group was given lithium, a standard treatment. One group was given a placebo. And the third group was given, let's see if I can pronounce this, desipramine, I'm going to go with, a newly developed antidepressant. The study was conducted over 3 years, with the results shown below. Is there evidence that either of the treatments improves the likelihood for successfully breaking a cocaine addiction? So we have 72 adults broken up into 3 groups, 24 in each group. All right. The number of subjects after 3 years with no relapse, well, desipramine certainly has the most, 14, lithium 6, placebo 4, so kind of looks like it, but again, maybe that's normal random variation, nothing more. Right? So what we need to do is look at this in comparison to the goodness of fit type of question. We could do a little, when do you do which? First of all, the big thing to notice is that this is actually categorical data. Is there a particular order to these 3 groups? No, we could order them however we want. All right. So one of the big differences with chi-squared is that it's one of the few tests that we can use on categorical data. Now, in the Is America Getting Older question in the previous video, there was one population, U.S. adults, that was divided into 4 age groups. Right? Now, age was the variable, so there's actually one variable that had 4 levels to it, and one population. Notice that in this question we have 3 different populations. That's important. All right? Each group represents a different population. The population of people taking desipramine, the population of people taking lithium, and the population of people taking a placebo. Now, in the Getting Older question, there was a theoretical ideal used to calculate the expected counts. Of course, how you calculate the expected counts is very important. And we had some theoretical model to use. Don't really have that in this example. There's no way of knowing how many subjects should have no relapses. I mean, that's an unknown. We have no model for that. So we can't do a goodness of fit test in the same way. So what we're going to be doing is comparing the 3 populations against each other. And our starting point is going to be that population 1 is equal to population 2 is equal to population 3. It's going to be our null hypothesis. You can kind of see where this is going. It's kind of like a 2-sample Z or T test where we start off by saying the 2 samples are the same. Only now we're doing it for the populations. And we could actually, we have 3 populations in this specific example. We could have 4, 5, however many populations you want to compare. Now I'm going to need to make some space, so I'll get rid of this comparison stuff. We're going to need to make a 2-way table, which is going to look something like this. And notice that this 2-way table is different than the data table. All right, we have our 3 populations. We have our 1 variable, which is relapse, but the variable has 2 levels, either no relapse or it does have relapse. All right, so we have to make sure to have a complete 2-way table, which of course we can add across and add down, and we get all kinds of good data. Now, I'm going to need more space. I'm going to take this question, I'm going to condense it a little bit. I think I'm going to get rid of this table. So there, condense that. I'll move that table back up. All right. And of course, this 2-way table is our observed counts. And what we need to do is start working towards our expected counts. Since the three populations are equal, it's reasonable to combine them into an average proportion of relapses. So that will look something like this, right? We have, all of the relapses over the total, right? Turns out to be a third. We can do the same thing with no relapses. And using these, which is really sort of by averaging out the populations, combining them and dividing by the total, right, we can get our expected counts. The way we're going to do that is by saying, well, a third of the group taking desipramine, so a third of this 24 is going to not have a relapse, and 2/3 will. A third of the lithium group will not relapse, 2/3 will. A third of the placebo group, 2/3, you get the idea. Do that multiplication, and it turns out we would expect 8 people to not have relapse and 16 people to relapse. And of course, if the populations are all the same, our expectations would be the same for all of them. Now, those are our expected counts. Those are our observed counts. We can now start the process. Question, do any of these treatments help people quit a cocaine addiction? All right, we have our chi-squared test for homogeneity of populations. We have to verify, of course. All right, we have our, is it an SRS, and the counts, the expected counts. Now, the subjects were randomly placed into the groups. So in that sense, there was good randomization, but all subjects wanted to quit the addiction. So there's actually a bias going on here, and so the conclusion will only apply to those addicts who want to quit. If you have an addict who doesn't want to quit and you start giving them one of these treatments, it may or may not have the same effect. And of course, the counts, expected counts 8 and 16, bigger than yes, or bigger than 1, yes, and they're all bigger than 5, so no problem with that. Verified with that limitation due to it being a voluntary group. Our hypotheses, of course, are that there's no significant difference between the populations. Right? That taking the desipramine or the lithium really doesn't do anything. Alternative hypothesis is that there is a significant difference between the populations. Now we get to calculate our probability. We, of course, need to calculate the chi-squared. Here is our formula. Now we have a two-way table. So what I did is I put in our observed and then our observed counts here and our expected counts here. Right? This is for the no relapse, and this is the expected no relapse. Those get combined there. And this is our observed relapse, our expected relapse, and that gets combined there. And so these are various components of our chi-squared test. The next thing to do would be to sum them all up. Again, in that formula, it's the sum of all the components. And it turns out to be 10.5. Next thing we need is our degree of freedom. Now, finding the degree of freedom with a two-way table is a little bit different. Right, we have the rows are our populations, how many populations we have. The columns are the levels we have for our variable, which are just rows and columns, really. And with that, we can calculate that for this, this is a degree of freedom of 2. With chi-squared and degree of freedom, we can use our chi-squared CDF. I'm not going to draw the chi-squared distribution this time. I already have the visualization from the last video. It's really always this. This is our lower bound, our arbitrary upper bound, our degree of freedom. And turns out that the probability is quite low. All right, going to need to make a little bit space here again. There we are. And we should be able to start our interpretation of significance for this probability. Now we have a 0.5% chance of drawing the sample, so there is sufficient evidence for rejecting the null hypothesis at a 1% significance level. All right, so there is a difference. Right? These aren't all the same. Right? There is a significant difference. What we'd like to know is actually which one makes the most difference. Again, once we either reject or fail to reject the null hypothesis, in chi-squared, there's always an extra step. We have to look at the data and see magnitude and direction. So just like before, I'm going to add just these two together and get our components for the three different populations. So if you added these up, you get 10.5. So we're going to use those as a way of finding magnitude and direction. What we're also going to be doing, the last time in the Aging America question, we looked at the counts to see what age groups were reducing in numbers and what was increasing in numbers. This time we'll use a percentage. For desipramine, right, what percentage didn't ever have a relapse? Well, pretty high, almost 60%. Lithium, a little bit lower. Placebo, even lower. So we're going to use those also as a magnitude and direction discussion. And we can conclude that because desipramine has the largest contribution, this 6.75, to the chi-squared test, and the greatest success rate, 58.3%, I conclude that it significantly improves the chances of breaking cocaine addiction, right, more than the other ones. We have to look at the component of the chi-squared and the comparisons here to make that conclusion. That's going to be it for homogeneity of populations.